Welcome to You Matter and Energy. Today we are looking at 2.2 ionic bonding and the crystal lattice. This deep dive is, well, it's our shortcut to understanding one of the most fundamental structures in all of chemistry.
It really is.
We're talking about how metals and nonmetals interact and, organize themselves into the materials that make up, well, everything from the Earth's crust to the salt you put on your dinner.
Right. Our mission today is really to uncover those tiny, unseen electrical forces that are quite literally holding your world together.
So where do we start?
We're going beneath the surface. We are defining the specific type of bonding that creates these massive, rigid structures, these crystals. And this is all about ionic bonds, where these really strong electrostatic forces dictate the entire arrangement.
Holding positive and negative ions together.
Exactly. In a predictable, highly ordered three-dimensional structure.
Okay, let's unpack this. When we talk about bonding, there's sharing electrons, that's covalent.
Yep.
And then there's this, I've heard it called the ultimate chemical divorce settlement.
That's a good way to put it.
Ionic bonding is all about a complete transfer of electrons. No sharing, it's a giveaway. And it almost always happens between a metal and a nonmetal.
And it's all driven by the need for stability. The metals, the ones on the left side of the periodic table, they have maybe one or two valence electrons they just want to get rid of.
It's easier to lose one than gain seven.
Precisely. They want to shed that outer layer to reveal the stable noble gas configuration underneath. And the nonmetals on the other side are, well, they're electron hungry, desperate to gain one or two to complete their own outer shells.
So let's use the classic example, table salt. You have sodium, a metal with one valence electron it wants to offload, and you have chlorine, Cl, a nonmetal with 7. It needs just one more. So sodium just, hands it over?
It literally hands its electron over to chlorine. The transfer is complete, and in that one move, both atoms achieve that stable state they were after.
And that transfer, it fundamentally changes them, right? They're not neutral atoms anymore.
Not at all. They become charged particles we call ions. The atom that loses the electron sodium in this case is now left with an overall positive charge. It has more protons than electrons.
And we call that a cation.
We call that a cation.
I always remember the silly little trick. A cat has paws, so it's positive.
It works, and what's really interesting is that the cation is always smaller than the original neutral atom.
Wait, really? It lost something, but it gets smaller?
It does. You've removed that whole outer shell of electrons, so the remaining electrons get pulled in much, much tighter by the strong positive charge of the nucleus. It becomes a denser, smaller particle.
Okay, that makes sense. So conversely, the one that gains the electron, the chlorine, becomes an anion, negatively charged.
And it gets larger.
Because of repulsion.
Exactly. You've added an extra electron, increasing the overall negative charge, so all those electrons start pushing each other away. The electron cloud just puffs out a little.
And this has to balance out, right? Like for something like magnesium chloride, MgClO.
Oh, that's a perfect example. Magnesium is in group 2, so it has 2 electrons to lose. It can't just give both to one chlorine atom.
Chlorine only needs 1.
Right. So magnesium has to transfer 1 electron to 2 separate chlorine atoms. And that perfectly balances the charges and gives us that 1:2 formula ratio.
So once these charged ions are formed, one positive, one negative, they don't just drift apart.
No, they snap together.
With this powerful, invisible force.
The electrostatic attraction, sometimes called the Coulombic force, that attraction is the ionic bond. It's just that universal law, opposites attract, but magnified at the atomic level.
Which brings us to strength. How do we measure how strong that bond is?
We quantify it with something called lattice energy. It's basically the energy you need to completely break the crystal apart, and it's governed by 2 main things from Coulomb's law.
Okay, what are they?
First is the magnitude of the charge on the ions, and second is the distance between them.
Let's start with charge. So more charge means a stronger bond.
Absolutely, a much stronger bond. If you compare regular salt, no clue, that's a +1 -1 interaction.
Right.
But then you look at something like barium oxide, BiOCO, that's a +2 -2 interaction. That double charge actually makes the attraction 4 times as strong.
4 times? Wow, so it has a much higher lattice energy.
Way higher. You need a lot more energy to break that bond apart.
So here's a question then. If doubling the charge makes it so much stronger, why isn't every ionic compound made of like +3 and -3 ions?
That is a fantastic question. It gets into material science, really. While a higher charge gives you enormous strength, the amount of energy you have to put in to rip 2 or 3 electrons off an atom in the first place,
Oh, the initial investment.
it becomes prohibitively high. So nature kind of settles for the easy win. +1, -1, or +2, -2 charges are common because the energy you get back when the lattice forms massively outweighs the energy you had to spend to create the ion.
That makes perfect sense. The best return on investment. So what about the second factor, distance?
Distance is all about the size of the ions, their radii. It's an inverse relationship.
So smaller ions mean stronger bonds because they can get closer together.
You got it. Smaller ions can pack closer, and that results in a significantly stronger bond. If we compare sodium fluoride, NaF, to sodium iodide, NaOi.
Fluoride is tiny, iodide is huge.
Exactly. The tiny fluoride ion can get right up close to the sodium ion, much closer than the enormous iodide ion can. So NaF has a much higher lattice energy.
And that strength has real-world consequences. We see it, right?
We do.
It's why ionic compounds have these ridiculously high melting points. Salt melts at over 800 degrees Celsius.
And that lattice energy isn't just a number for us. Physicists and engineers use this idea when they're designing, say, ultra-hard, heat-resistant ceramics.
For what, jet engines?
Jet turbine blades, furnace linings, stuff like that. They are actively seeking out those high-charge, closely packed ionic compounds to get the properties they need.
Okay, so once these super strong bonds form, they don't just stop with a single pair of ions.
Not at all. See, a positive ion doesn't just attract one negative ion. It attracts them from every direction. Up, down, left, right, front, back.
So they can't exist as just discrete molecules.
They can't. Instead, they just keep building up into this massive, repeating three-dimensional structure, and that is the crystal lattice.
It's like the ultimate electrical checkerboard.
That's a great analogy, or a 3D jungle gym. Every positive ion is trying to surround itself with negative ions, and every negative ion is trying to surround itself with positives.
Maximizing attraction, minimizing energy.
The lowest possible energy state for the whole system. And since it is this huge continuous structure, we can't call NaCl a molecule.
Right, that's where the term formula unit comes in.
Yes, the formula unit just describes the simplest whole number ratio of ions in that massive structure. It's our sort of basic currency for talking about them.
So how do you even study a structure that big?
Well, we look at the smallest piece that represents the whole thing. It's called the unit cell.
The repeating block.
The repeating block. If you take that unit cell and just stack it perfectly in 3 dimensions, you reconstruct the entire crystal. Think of it like a single tile in a mosaic.
Okay, so the unit cell tells us how all the ions are arranged.
Exactly. For a simple structure like sodium chloride, it's based on a simple cubic packing arrangement. But what's kind of surprising is that even though they pack pretty densely, there's still a significant amount of empty space in there.
It's not 100% efficient.
Not even close. The packing density is directly tied to the relative sizes of the cation and the ania.
So they fit together like different sized marbles, but the one rule is that positive and negative must always be alternating.
That is the primary constraint. And that brings us to our next key concept.
Which is the coordination number.
Hmm?
Now this sounds technical, but it's actually just counting. It's the number of nearest neighbors of the opposite charge that surround any given ion in that lattice.
That's it. So in our classic NaCl crystal, if you pick any single sodium ion and you look around it,
You'll find 6 chloride ions.
exactly 6 chloride ions at the closest distance. And if you pick a chloride ion, you'll find 6 sodium ions. So the coordination number for both is 6.
But if the ions are different sizes, that number can change, right?
It has to. The size ratio is key. A much larger central ion can physically fit more neighbors around it. For instance, in cesium chloride, the cesium ion is bigger than sodium.
So it can fit more neighbors.
It allows it to fit 8 chloride neighbors around it, giving it a coordination number of 8. But crucially, the ratio of the coordination numbers must always reflect the formula unit.
Can you give us an example of that?
Sure, take titanium dioxide, TiO. The formula is 1 to 2. In its crystal, the titanium ion, TiO, has a coordination number of 6, but the oxygen ion, EiO, only has a coordination number of 3.
Ah, so the ratio is 6 to 3.
Which simplifies perfectly to 2 to 1, exactly matching the formula. It's this beautiful, self-organizing balance that the charges enforce.
Okay, so this structure is rigid, strong, highly ordered. How does that perfect order explain why a salt crystal shatters if you hit it?
That is the brittleness. It's the downside of perfect order. If you strike a crystal with a hammer, you physically shift the layers of the lattice just a little bit.
You slide them over.
And when those layers slide, you suddenly force ions of the same charge to line up. Positive next to positive, negative next to negative.
And likes repel.
Likes repel violently. You get this massive repulsive force that acts like an electrical sledgehammer from the inside, and the entire crystal just fractures. It shatters instantly.
It can't bend or deform like a piece of metal can.
No give whatsoever.
That makes perfect sense. The same force that holds it together so strongly is also what breaks it apart. Okay, final property. Conductivity. A block of salt is an insulator, but salty water conducts electricity perfectly.
And this is all about the state of the ions. In the solid form, it is a poor conductor. The ions are locked into that rigid lattice. They can't move.
No free movement, no way to carry a current.
Right. But if you melt it or if you dissolve it in water, the lattice breaks apart.
And that's where the word electrolyte comes in.
That's it. The ions, like Na-U and Clo, become free-floating in the liquid. And these mobile charged particles can now carry an electrical current through the solution,
They become the transport mechanism.
making it an excellent conductor, an electrolyte.
And water is especially good at pulling that lattice apart, isn't it?
Oh, it's a master at it, because water is polar. The slightly negative oxygen end of a water molecule grabs onto the positive cations.
And the positive hydrogen ends grab the anions.
Exactly. The water molecules just surround the ions and escort them away from the solid structure, breaking those powerful lattice bonds and letting them float free. It's why electrolytes are so vital for everything from sports drinks to how your own nervous system functions.
So we really covered the whole journey. We started with the electron transfer from a metal to a non-metal,
A great exchange.
then the powerful electrostatic force that creates all that stability, and finally the massive repeating crystal lattice structure itself, which we can describe with unit cells and coordination numbers. And understanding that lattice explains why these materials are so strong, why they're brittle, and why they become electrolytes when you dissolve them.
And if we just connect that to the bigger picture for a moment, you have to remember that the crystal structure of any ionic compound must perfectly reflect its formula unit. It's not random. Whether it's salt or a complex mineral, the geometry, the coordination numbers, it's all predetermined by the simple rule of electrical charges seeking stability.
It's an incredible self-organizing power.
It really is. It's fundamental physics happening at the atomic level, dictating the properties of the materials all around you.
A massive thank you to the Geeky gamer science teacher for creating this deep dive.